For the last, I guess, I actually don't know, how hard is the 5:30 deadline? Is it the bus deadline?
I think, yeah, the bus is going to leave at 5:45.
Okay, so just to, we'll stop at 5:30. I'll give myself a 5 in the morning. And so I thought, this thing is impossible to write down. I thought I would just, outline like 1 or 2 questions. I think it's all we have the time to discuss at all that I noticed. And actually, before I start, I want to thank all the speakers before I start. Because that sees everything I'm about to say. Actually, I'm hopefully not going to say much. I hope you guys are going to say everything. And so
you've said a lot about not saying anything.
So I'm not going to say, no. So I think I'm going to write just 1 or 2 questions down, and then we can discuss those and leave it like that. So I thought this morning it was very interesting to see how the number density potentially of very massive ellipticals changed. And then couple that with the idea that the IMF may change towards the massive end. So I'm going to write this as, what are the effects of IMF variations and the change in the mass function
It's more to change the luminosity function.
Well, it was both. I mean, looking at her plot, she had a mass function and a luminosity function. So the observable is a luminosity function.
Right. But that really changed. The IMF is still an inference that.
That's right. So that's absolutely right. Let's do the luminosity function, and then I think that's right. And I didn't write that yet, so LF, right? Of things like log m. Well, actually, I won't do that now because we're reducing luminosity function. So very luminous objects, right? So what's the implications of? What are the effects of that thing on things like galaxy growth, right? Of massive galaxies, both in mass and in size, from Z of 1, right? Since basically Bell 2003, we've been building this picture of how massive galaxies have been growing since Z of 1. How does that change if all of a sudden we take the biggest galaxies today and increase their numbers by a factor of 16 at the most massive end? Because it's something like a factor of maybe 4-ish from Mariangela's work, and then maybe another factor of 2 to 4 from the stellar mass from the IMF changes. What?
Maybe factor 2.
2. So a factor of 8. Fine. So you've increased them by a factor of 8-ish, right? So
galaxies,
4 from her and 2 from you.
I don't see that the galaxy is actually adding the mass at enormous radii. There's no idea whether the IMF there is also changing when the IMF is
okay.
The center of the velocity dispersion is high. So this is quite an extreme. Maybe it's good to be.
So maybe it's, yeah, so it's slightly provocative is good, right? So galaxy growth in mass and size.
It's actually that mass that you're adding at the outside comes from low mass galaxies. So
that's right, so maybe it's not,
with IMF variation.
Well, but it's not as if it's new mass that is necessarily coming in. It was mass that we just hadn't taken pictures of.
And the thing is, we don't...
Well, we took the picture, we just didn't analyze.
And we don't know what the IMF is in the things that end up in the envelopes of
exactly.
right?
Right, but this certainly would be an argument for gradients in the mass to light ratio. Just if there is a difference between the average per Denninger mass and the mass, the IMF associated with the given.
No, but the IMF is at low mass end, and there's no color.
I don't think color.
So, what do we need? What does this change in terms of our picture of how both the stellar mass grows in a total sense and how the size evolves? Because we have things like these compact galaxies dropping their numbers drastically, and now you're thinking that I actually don't know, does the size evolution of the most massive things now change a lot?
So I have a paper I show that you change the luminosity, but you change the size. So after the relation is just a slightly little bit cool with a high hand, but more or less the relation.
Because the mass size relationship isn't really, or the luminosity size relationship.
Both change.
Okay. And what about, we had talked at lunch, some of us talked at lunch a little bit about whether, what this requires for AGN feedback, what this changes for AGN feedback, and Rachel mentioned this in her talk. So I just wanted to open this up. Well, no, Rachel made the claim that it makes a big difference, right? So, you said that, okay, now we have to actually, if we have many more of these more massive things, we have to turn down our quenching.
Yeah.
So if I remember what you told me earlier was, it just so happened at work that you had the right quenching to get the mass function, and you got the quench fractions right, but now.
Just remember, so there were tremendous mental gymnastics that was going into trying to get the semi-analytic and other models to match the mass function lack of growth at the massive end. Because the mergers happened,
Right.
so they had to figure out where to put those stars, and so they ended up putting in the intercluster light.
We actually don't put that much in the intercluster right now, we only put 20% for merger.
But for a while, it was a lot. A lot of models have a
And
lot.
also the empirical models need more, 40, 50%.
More,
Yeah,
so
I mean,
yeah, no,
So that will change, that number will come down.
I think you have to step back and retune if you.
But aren't there two competing
So I don't know
things?
that
On the
this is
one hand,
functional
you need
necessarily.
more of these galaxies. On the other hand, the specific star formation rates often go down because the star formation rates are still low.
Yes,
Right, so can you get the mass function and the quench
So you
fraction
need to quench them more and less
simultaneously?
at the same time.
Yeah, that's the problem. No, that's the problem. You're quenching less because you have to get more massive galaxies, but you need to keep the passive fractions the same,
Right.
because those aren't changing.
But most of
Right,
that
and
mass,
that's a problem.
with agent feedback, you make sure that most of that mass growth does not have to do anything with star formation. It has to do with how many satellites you create. The one thing that's very poorly modeled in all semi-analytical models is how they treat satellite galaxies, stripping, what fraction of the merger goes into that. They just need to change that, but they need to change it anyway to get the right fractions correct. So I think the treatment of satellites, there's so much freedom there that I think it's fairly easy to just tune it to get it right.
You can say that,
I
but,
don't know.
I think we need to do it. We need to do the exercise, and we have hydrodynamic simulations as well now that are, at least with the Zuman simulations, they're treating those processes.
Is that just an extra degree of freedom? You treat the satellites?
No, you don't have, it's not like you have complete freedom, right? They're falling into the gravity, more or less know what's happening, at least the big ones, right? The
I
biggest
agree that
ones,
simulations basically should take it into account. In some of the models, we have a lot of freedom in what we do with those things.
not so much if you're using n-body merger trees.
Yeah, but when do you strip? Do you ever strip any
Sure,
satellite?
sure.
Well,
You
how
have
much do you
constraints
strip?
on that.
How much do you strip?
You have been one of the people that have provided those constraints.
Yeah, but I also
You
believe
can't
that.
just dump infinite amounts of stuff into the ICL, right? We have some idea of how much mass is in the ICL.
Exactly, but the only thing that now changes, that part that we called ICL now has been called stellar mass, and now we can actually, we don't have to put it into, the stars are there, we just have to label them differently,
No,
Maybe.
in
so
first order.
Maybe,
So-
I'm not sure.
when we measure the light that now we see that is a little bit brighter, it's not because we are measuring the ICL. That is what I want people to do.
But
If
in the
it's
old
really
days,
profile, it's
any
different.
amount of stars that was not counted as part of the galaxies was called ICL. That
People
was
have measured
the
ICL.
definition of ICL.
Yeah, so one thing is the definition of ICL, okay. Another thing is to say you are using the wrong profile to measure your antecessor brightness of galaxy. So what I'm saying is that when we measure now the profile is that Sloan, they have to measure millions of galaxies, okay? They use just a molecular profile. Molecular profile is not the right profile to use now.
But I thought from our discussion, for Baldry also uses a Sursage
Yeah.
fit, and you
So the
said,
luminosity is
and
the
he
same.
and he gets a very different result from you, and you said that's because the mass to light ratios are different.
The luminosity function, Baldry and mine from the Cersei.
Exactly, are the same.
Okay.
So then it's mass to light ratio,
And
not.
it's because the
Yeah.
Cersei is the right, or is a better profile, okay, than the Devacular. So if I use my Cersei, Baldry Cersei, we will get the same result, okay? If instead you use the Devacular from Sloan or the Petrosian from Sloan, you get different result. That is just because they don't fit properly
But the difference with Baldry is not how you fit, it's mass to light ratio.
The difference between in the stellar mass, don't confuse the luminosity.
Yeah,
with
stellar mass.
function. The stellar mass function
That's what
depends
I'm talking
on the M over L. M over L come out from stellar population models. Okay. If you use different stellar population model, if you use Blanton, template, or you use Marston template, there is a huge difference.
So you should really have three things, right? You should have, first, how much light is in the galaxies.
Yeah.
Exactly. That is the data.
Photometry.
That is the
Then
data.
you have to convert to stellar mass, and that depends on the stellar
That
population
is-
models, as well as the IMF.
The spatially resolved
Right.
population.
Yes.
That is why
And
my
spatially
opinion-
resolved IMF.
In my opinion, observer should just give the luminosity function.
No, but
Except I'm going to channel Danilo Marcazzini, who says that when he writes a luminosity function paper, nobody cites it, and when he writes a mass function paper, everybody cites it, so you give both.
True. So that should be the model that they assume, this stellar population, they assume so all the other assumptions should made by models. The data is, so that you just measure the data without any, then you say, oh, is there a mass function? But there are so many assumptions there in the data that everybody measures what they want.
Okay, I'm gonna.
I was just say, if you want to understand AGM feedback, I think that's the wrong thing to look at. Because you're adding things that are accreting from low mass galaxies. Look at what happens in the central 30 kpc where everybody agrees, and look at the gas in the X-rays. Then I think that's a much better way of understanding AGM feedback than getting this mass function out to 300 kpc integrated, right?
Okay, I'm gonna ask 2 more questions of which we probably don't have time to answer either. Or does anybody else have something they would like to say?
I have another thing that if I can add.
Yeah.
That in my opinion, another problem that I would like to run Rachel also is, I don't know, do you have also the velocity dispersion? Okay. So because if we look at the velocity dispersion of these compact galaxies, high energy galaxies, also that its distribution is high. You know, you go from 500 kilometers per second to, an average of 250.
Can you speak louder so that we're being in the back?
Okay.
Because I want to make sure it's not just a conversation with you two. I want
Yeah,
to.
so the velocity dispersion of these high radiation galaxies tend to be on the high side. Okay. So now, based on a few talks, sometimes they said, oh, the very massive galaxy, they form through major merger, prime merger. Because they see galaxies that are almost equal, very close. Now, the problem is that based on the recent simulation, when you have a major prime merger, you are going to increase your velocity dispersion by a factor of 30–40%. Okay. In the local universe, we don't have galaxies. They are very rare galaxies that we have with velocity dispersion of 320, so they are very rare. Most of the galaxies in the local universe, they have velocity dispersion below 300 kilometers per second. So that means it's still
There's another effect in the models, which I didn't have time to discuss, but this relates to Aaron Button's talk. So if you have dissipation, that can actually push some of the dark matter out. So there's also a trade-off between the velocity dispersion that you measure, depending on whether it's formed in a dry merger or a wet merger, because if it's a dry merger, it'll have relatively more dark matter, and if it's a wet merger, it'll have relatively more baryons. So you end up getting this very weak evolution in the velocity dispersion, in spite of the large size. But it's partly a trade-off between the dry and wet mergers.
Okay, I'm going to see 2 more questions so you can think about it on the bus, but we're not going to have time to talk about them. Why does age abundance matching work, or does it? And are early type and late type meaningful categories to classify galaxies? Or what does it mean when you say early type and late type?
No to the last.
The answer is
Well-
only if you're talking about morphology. And even then,
So spectral, I would personally say spectral, using the word early and late type for a spectral classification is a bad thing.
yeah,
Yes,
no,
I completely agree.
use quiescent and star forming for spectral
Yes.
classifications or color classifications. Use only early and late type if you're talking about morphology. Let the timeline or calibrated variable.
And define what you mean by early and late
Define
type.
what do you mean? Where's the dividing line?
Okay. I think we have to stop now, otherwise you're all walking down. It's a beautiful walk. But
That's not a bad idea.
It's actually-
Cleared up. It's nice.
Well, probably wet.
So,